Interdimensional travel is the stuff of science fiction. At least in 2023, there's no way I know of contacting a Jason in a parallel universe. Though we'd probably both like talking about how good those fits are in When Harry Met Sally. But in the realms of geometry, math does give us a way of transporting across 2 and 3 dimensions. For example, consider 6 squares arranged in a cross shape in 2 dimensions. If we think about connecting these same 6 squares by their edges, we can transport the shapes from the 2-dimensional world into the 3-dimensional world. Those original 2-dimensional squares are still there, but how we're using them kinda turns them into portals between 2 and 3 dimensions. More generally, when we're dealing with 3-dimensional objects, we call these outside boundaries/portals surfaces. And being able to move between 2 and 3 dimensions with this type of thinking helps us learn more about shapes by finding their area, which we call surface area. Whether it's painting, constructing, wrapping things, or even just designing a soda can, understanding surface areas is essential to designing the world around us. And even navigating the world itself, since most of us live our lives on the surface of planet Earth. I'm Jason Guglielmo, and this is Study Hall Real World College Math. Last episode, we talked about area, which is the amount of space a 2-dimensional shape takes up, and surface area is pretty similar. In fact, it has the same units, but as the name suggests, it's the area of the total surface of some 3-dimensional object. Or in other words, surface area is the area of each side on the shape added together. Imagine a box you want to wrap up in paper. The surface area of the box is the amount of wrapping paper you need to cover it. Well, besides the folded parts that I can never get right. And as we showed at the start, it turns out a lot of what we learned about dealing with the areas of simple shapes in 2D comes in handy for surface areas too. To see how, let's head over to Arslan, who works in the manufacturing department at Hamilton's Stout Brewery. Hamilton's is about to enter the mass consumer market by selling their stout in cans, which they'll make on site. But before they can get started, they need to know how much material they will need for the process of canning and shipping the cans to grocery stores. First up are the boxes the cans will be shipped in. In math speak, the shape of a box is a rectangular prism, because the faces of the box are, you guessed it, rectangles. Hamilton's boxes are going to be 17 centimeters in length, 20 centimeters in width, and 13 centimeters in height. Remember, the surface area of an object is the area of each side of the shape added together. So, looking at the design of the box, the amount of cardboard that makes up each box corresponds to the box's surface area. And calculating that will tell Arslan how much material he will need to forecast costs. Before we get bogged down in details, it helps to first look at the shape we're considering. A rectangular prism has 6 faces. In fact, these 6 faces form 3 pairs of identical opposing rectangles. And without writing anything down, we're already approaching our answer and a formula for finding the surface area of any rectangular prism. Last episode, we saw the formula for a rectangle is its length multiplied by its width. There's one small catch here though. The different dimensions of each pair of rectangles for our box aren't just the length and width of the overall box. But by taking a look at each pair of sides, we can quickly work out what dimensions we need to use for each. For one pair, it's the length and width of the rectangle, as usual. For the other, it's the width and height. And finally, there's the pair with length and height. So, first we can calculate the corresponding areas of these rectangles. Then we can double them because each one appears twice on the box. And finally, all we need to do is add them up. And we've got a formula for the surface area of a rectangular prism. Crunching the numbers for the boxes Hamilton's will be shipped in, Arslan finds the basic shape of each box requires 1,642 centimeters squared of cardboard. Now there's one last detail to consider in this particular situation. As well as the cardboard that makes up the sides, the boxes also have an extra bit that make up the flap attached to the lid, which tucks into the box to hold it shut. In Arslan's case, it's the same area as one of the rectangular sides he calculated earlier, so he adds that amount to the surface area we just found for his final answer. With the packaging out the way, next up on Arslan's agenda is the aluminum cans for the stout. The cans are in the usual shape with 2 circles on each end that are joined together like in the shape of a pipe. That's a bit of a complicated description, but we call this shape a cylinder. Specifically, a can of Hamiltons will be a hollow cylinder made from sheets of aluminum. Each circle on either end will have a radius of 33 millimeters, and the can will have a height of 150 millimeters. So, similar to the boxes, Arslan wonders how much aluminum each can needs so he can predict manufacturing costs. Once again, making some observations is a powerful tool for tackling the problem. We can identify shapes we already know how to deal with to help us find our answer. First up, notice that the ends of a cylinder are just circles. That's great news because now we see the total surface area of the cylinder will involve adding the areas of these two circles. Based on what we learned last episode, that'll be pi times the radius squared for each circle. But the bit that curves around the cylinder isn't so obvious. The trick here is to imagine unrolling this curved section of the cylinder out into a flat sheet, like it was a rolled up piece of paper. That gives us a rectangle, which we're well equipped to deal with. Now we just have to find this rectangle's length and width. The length is fairly simple since it will be the same as the height of the cylinder. As for its width, notice that before we unrolled this curved area, it wrapped around each of the circles at the end of the cylinder. That means its width is the same as the circumference of each circle, which in a previous episode we found to be 2 times pi times the radius. So the circumference of our circle is the width of this flattened out rectangle. And that's all we need to work out the area of the curved bit of our cylinder. Plugging this all into the rectangle area formula, we see that its area is 2 pi r times the height of the cylinder. Now all we have to do is add this area to the area of our two circles, and we have ourselves a formula for the surface area of a cylinder. Plugging in the numbers here, we see that each can needs about 38,000 millimeters squared of aluminum. Finally, Arslan moves on to a little known secret in the canned stout industry: the widget. We'll spare you the full physics lesson, but the widget is a little plastic ball that sits inside each can of stout. When you open a can and pour it into a glass, the widget releases nitrogen gas from the canning process and helps the stout develop that classic creamy head on top of the drink. Of course, a ball shape gets its own math name you're likely familiar with: a sphere. The size of a sphere is defined by the distance from the center to its surface, which is called a radius, just like for a circle. In this case, the radius is 15 millimeters. Now, to hold the gas, the widget has to be hollow. That means the amount of plastic needed to make this little sphere will be based on, you guessed it, its surface area. What a wild coincidence. Although, at this point, I have to come clean. Getting a nice, neat formula for the surface area of a sphere is pretty involved. Many approaches use calculus, although a few use some clever geometry tricks to get the same answer. It actually uses a similar trick to the cylinder, but we'll leave a link to the full explanation of how it works in the description. The basic idea is that the surface area of a sphere is the same as the surface area of a cylinder that's the same height as the sphere, minus the bits from the flat circles at the ends. Now, from the shape of the ball, we can note the height of the sphere is twice the radius. And if we take a look at how the cylinder wraps around the sphere, the width is the circumference of a circle with the same radius. And once again, we find circumference using 2 pi times the radius. So we can put all this information into the part of the cylinder formula that comes from the rectangle formula. When we multiply these together, we get 4 pi r squared, a general equation for the surface area of any sphere. With this shiny new formula for the surface area of a sphere, Arslan calculates that each widget's surface area will require around 2,800 millimeters squared of plastic. And that gives him a good idea about the amount of plastic he needs to produce the widgets. With that, Arslan has tackled 3 of the most important material inputs for canning and distributing Hamilton's excellent brew. Of course, rectangular prisms, cylinders, and spheres are only 3 of the many 3-dimensional shapes whose surface area we might want to calculate in different scenarios. You might need the surface of a pyramid, or a cone, or even the funky 20-sided dice in Dungeons and Dragons. But in a lot of these cases and beyond, the ideas we've developed here will help. It's all about breaking the objects down into simpler shapes that are easier to deal with. For the flat bits of a surface, we can calculate their areas as though they were just 2-dimensional shapes and add them up. And for some curved surfaces, a bit of ingenuity can get us a long way, like we used for cylinders. But in 3 dimensions, surfaces are only one part of the game. Next episode, we'll dive deeper and study how to calculate the amount of space taken up by 3-dimensional objects when we take a closer look at volumes. Thanks for watching Study Hall Real World College Math, which is produced by Arizona State University and the Crash Course team at Complexly. If you like this video, give us a like and subscribe. You can learn more about ASU and the videos produced by Crash Course in the links in the description. See you next time.